Okay, good day. So we will have another example. So this will be our third example. So we will concentrate here at problem 5.5. Okay, this is also from the book of Mechanics of Materials by Andrew Peitel and Jaan Kyosalaas. Okay, so find the maximum bending stress in the rectangular wooden beam. And this is your beam. Okay, it has a 180 libra per foot uniformly distributed load, and then 1,200 libra upward point load at A, and then obviously it is a cantilever beam because it's free at one end and it has a fixed support at the other end. And then it has a base of 4 inch and a depth of 8 inches. Okay, so without further ado, I will go concentrate on its solution. Okay, so I have already here a solved solution. A solution in this problem. Okay, I already solved it in advance, and I will just discuss how did I arrive with those solution. Okay, so here, so this is the solution. Okay, so I just copied the beam. Okay, so since we have a fixed end, so since for a fixed support, okay, for a fixed support is it has three reactions. It has both horizontal and vertical reaction and also a moment reaction. So I put here Bx as the horizontal reaction at B, By as the vertical reaction, and Mb as the moment reaction at B. Okay, so I just put here its base is 4 inch and its depth is 8 inch. Okay, so here we go. So I actually started. Okay, so before we can compute its maximum bending stress in this wooden beam, so first we have to compute its reactions at the supports. Okay, so in order for us to do that, we need to construct the equilibrium equations. Okay, so my first equilibrium equations that I construct is summation of forces along horizontal or x direction is equal to 0. Okay, so I assume that to the right is positive. So here, this as we can see in the beam, there is only one horizontal reaction. Okay, which is Bx. Okay, so B sub Bx, and there is no other load. Okay, so we have negative Bx is equal to 0. So therefore, Bx is equal to 0. And then we have, and then I sum up forces along y direction. Okay, so I assume that upward is positive. So we have, okay, from the drawing, we have By plus 1,200 since this load is upward. So it's positive. And then minus 180 times 12 since we have a distributed load of 180, and then we have actually the length of this. Okay, so I forgot to put. Okay, it has a length of about it has a length of about 12 feet. Okay, so that's what. So that's why I multiply 180 by 12. Okay, so by algebraic manipulation, so this, okay, 180 times 12 is 2,160. So if you transfer it to the right, it will become positive, and this 1,200 will become negative. So by simplifying, we get By is equal to 960 libra. So since it is positive, so our assumed direction of By is correct. So it is upward. So the third one is I sum up moments at A is equal to 0. Okay, So here, I assume that counterclockwise as positive. Okay, so looking at this drawing, since we sum up moments at A, so let A will be your steady point, and the rest of the drawing, in this drawing, the rest of the forces will make the beam rotate. Okay, so relative to A, this 180 libra per foot will move, will rotate clockwise. So we have negative. Okay, so since it is clockwise, negative. Okay, so 180 libra per foot, we multiply it by its length, which is 12, and then we multiply it by its moment arm. So its moment arm is just 1/2 of its length. So 12 over 2. Okay? And then plus MB. Since MB relative to A, so this MB will rotate counterclockwise. So it's positive. And then so we have computed BY as 960. So your BY will be 960, okay, times 12. Okay, so here in this portion of the solution, I just simplify negative 180 times 12 over 2. So we got 12,960 plus MB. And then previously we computed the BY as 960. So plus 960 times 12. Okay, so this 960, this BY relative to A will rotate counterclockwise. So it's positive. Okay, so to make the long story short, so we got MB is equal to positive 1,440 libra foot. So since we got a positive value, so therefore our initial assumed direction for MB, which is counterclockwise, is correct. So it's 1,440 libra per foot clockwise. Okay, so then we can now draw our shear and moment diagram. Okay, so here, okay, so what I did is I composed, okay, I construct shear and moment equations. Okay, so since we have an upward force 1,200, so its shear from 0 to 12 is 1,200 minus, okay, since we have a 180 libra per foot distributed load, so 1,200, which is this, okay, 1,200 minus 180 times x. Okay, so please review your shear and moment diagrams. Okay, how to construct the shear and moment equations. Okay, so this is what I get. So V equals 1,200 minus 180 times x, and then your moment is simply 1,200 x minus 180 over 2x squared. Okay, so in order to check whether your shear and moment equations are correct, so if you differentiate your m, you will get your v. Okay, so here if you differentiate 1,200x minus 180 over 2x squared, you get the equation of v. Okay, so it's correct. Okay, so then I computed on what a value of x will your shear equation will be equal to 0. Okay, so I computed, so I equated this to 0. So I got x equals 20 over 3. Okay, so at that point, okay, this is the point, x equals 20 over 3, where your v will be will become 0. Okay, so to clarify, this is actually a 1 degree. Okay, so therefore it is actually a straight line. Okay, so it might not be exact. Okay, so it is supposed to be a straight line, a straight line with a slope. Okay, it's supposed to be a straight line with a slope. Okay, so it is linear. Okay, it's not curvilinear. Okay, so from that on, since we get x where the value is of shear is 0, so we substitute it to the moment equation so that we will get the corresponding moment at that point. Okay? So if V is equal to 0 or your shear is equal to 0, automatically your moment at that point is at its it's either it is at its maximum or minimum. So here we get the maximum, which is, okay, 4,000 libra per foot. Okay, so we just substitute x equals 20 over 3 to this moment equation, and we got 4,000 libra per foot. Okay, so this is, okay, so these two governs these two diagrams. Okay, so from that time, okay, so we get your maximum moment as 4,000 libra per foot. Okay, so we will use that to compute what is asked, which is the maximum bending stress. Okay, so we have bending stress maximum is equal to M max, or the maximum moment, over S. Okay, so your S here is the section modulus, and since it is a rectangular beam at cross section, so your S will be equivalent to BH squared over 6, where your B is 4 and your H is 8. Okay, so you just substitute and you got 128 over 3 inch cube. And then you got maximum bending moment. Okay, you will get is equivalent to, okay, to M max over S. Okay, so your M max is equivalent to 4,000 libra per foot. Okay, I multiplied it by 12 because 12 12 inches per foot. Okay, so I multiplied it by 12 inch per 1 foot, in order that the 4,000 times 12 will become libra inch. Okay, libra inch, because your S is in inch. Okay, so what we got here is 4,000 times 12 over 128 over 3. So we got the maximum bending stress equivalent to 1,125 psi. Okay, so this is the answer, or it might be equivalent to, okay, so we convert it into KSI by dividing it by 1,000. So we got the maximum bending moment as 1.125 KSI. So this is our answer. Okay.